Very good morning. Let us take a small example of composition table. The question here says that G is a set comprises of 1 omega square. We have to check whether it is an abelian group or not under multiplication operation. And the condition is 1 omega square are cube roots of unity, which is equivalent to omega cube equal to 1. So first we have created the composition table using 1 omega square. So the column headers 1 omega square, the row headers 1 omega square. Then we are designing the Cayley's table here. 1 into 1 is 1, 1 into omega, 1 into omega square, omega into 1 omega into omega square, omega cube, which is equal to 1. Omega square into 1 equal to omega square into omega equal to omega cube, which is equal to 1. Omega square into omega square is equal to omega cube into omega. So omega cube is 1, so it will be omega only. Now after that we have to check whether it holds the closure property or not. So if you look at the elements of the set 1 omega square, after the multiplication operation also all the set members are same only, 1 omega square. So it holds the closure property, so it's an algebraic structure. It holds the associative property, so it holds the semi group property. How? The Cayley's table will not help us here. You can check this 1 omega square as 3 elements A, B, C, and you can check their associative property. After that, whether it's monoid or not, for that you need to check the identity. For identity, what you have to do is you have to check the matching rows and the matching columns. So let us say the matching row is this 1 omega square. Okay, so 1 omega square. So row 0 and row 1 are matching. Row 0 and row 1 are matching. So the extreme element of this is 1. So 1 will be the identity. Similarly, column 0 and column 1 are matching. So the extreme element again is 1. So the identity is 1. After that we need to check whether it's group or not. For checking whether it's group or not, we have to check the inverse. For inverse we have to look at identity, and after marking the identities we have to check the top extreme elements. So here identity is 1, and identity is 1. So if you take the top extreme elements, 1 inverse of 1 is 1. Similarly here inverse of omega is omega square. Similarly inverse of omega square is omega. Once we check the inverse property and assure that it is group, we need to go check whether it's abelian or not. For that we need to check the commutative property. For checking the commutative property, we have to put a diagonal here from this binary operation, and we need to check whether symmetry is there or not. So 1 omega square 1, omega square 1. So there is a symmetry of the non-diagonal elements. So that's why it is abelian. Thank you.